So, as Avi said, I'll tell you something about absorption method and also Ramsey theory, which are two major topics in extremal combinatorics. And I'll also tell you of an application of the former to the latter. So, first I want to say that I'm going a bit against the flow here. So I'm talking about two topics in a single talk, instead of talking about, well, a single topic or one or more talks. I just want to say that the reason is not that there is not enough material. You could fill full courses worth of material with either of these topics. And the reason is I have a nice story which should kind of fit hopefully within 2 hours and give you a bit of a flavor of what kind of things people look at in these two topics. So the first half of the talk is going to be about the absorption method, which is this amazing method from extremal combinatorics, which has found some really remarkable success stories over the past 15 years or so. So to make Avi happy, I have the customary board full of citations.
You made all that happy.
So I want to say that this is just the tip of an iceberg. There is really an amazing amount of results that people proved using absorption ideas. So not everything here is really using the bona fide, what's referred to usually as the basic absorption, but all of it is using some kind of absorption ideas. So also I want to point out so that kind of there is a lot of cleverness that goes on. So somehow absorption method it allows you to convert asymptotic results to exact ones, but still you need to put in usually quite a lot of work and cleverness into actually getting this to work. So the name is usually attributed to Rodel, Ruchinsky, and Szemeredi, who first gave it the name and codified and kind of systematically studied it, although there are quite a few applications that happened before, and I'll actually talk about some of them in the talk later on. So also I quite like that around 2012, there is a nice survey by Szemeredi, which he calls, "Does laziness pay off?" And the idea is somehow that since you're converting asymptotic results into full exact ones, then in some sense, you're not doing the hardest step of the argument. You're just kind of bootstrapping yourselves to the top. So a nice picture is kind of, imagine you're climbing a mountain, you're 95% there, you can kind of see the top, and then you call a helicopter to bring you to the top. And of course, building a helicopter is not easy, and that's kind of what absorption method does. So the plan for the talk is to tell you first in kind of high level what absorption method does, and then give you a few examples and illustrate how it actually works on some simple, nice examples. So rather than showing you the most flashy of these results, I'm more going to focus on explaining how you actually do that, because some of these most flashy results are approaching 100 pages. So kind of building a helicopter is hard. There is a lot of theory going into it. And my goal is to give you a flavor and kind of an idea behind all of this absorption stuff. So good, so let me now tell you this. Let me tell you this high-level overview of what absorption method does.
Everybody's listening to you. Now everybody's trying to imagine what was the next book.
Yeah, well, if I could use the side ones, I would have more freedom, but so anyway. So yeah, so I'm going to illustrate it in the setting of decomposition problems, which many of these examples in the background are precisely working on them. This is a large class of problems, both in combinatorics, but they appear all over the place in mathematics, also computer science. So just finding an error correcting code is pretty much a decomposition problem of your message space. It also pops up distributed computing, design theory, design of experiments. There is quite a long list. They're kind of nice and natural. And they just add, the general question asks, given some kind of large structure, can you decompose it into substructures which should have some kind of useful properties? And what I mean by useful depends on what you're trying to do. So that's kind of the picture we'll be having. And as I said, the prerequisite for using absorption is that you can prove an asymptotic result, by which I mean, so let's call the structure S. And I mean that you can kind of decompose whichever structure you start with in the whatever way you're looking at, up to maybe some kind of tiny leftover piece R. So suppose that we can do that. I mean, it's in no means trivial, but it's usually much easier than really perfectly decomposing your structure. And for quite a few results in the background, these results existed for quite a while before. So the first step, and somehow the main and really the key step of the absorption method, is to find the structure which we call an absorber. So an absorber is a substructure. Let me also draw a picture. So here's again our structure. I want to find the substructure A. It should be kind of smallish, but the key property it should have is that it can deal with any kind of it can absorb any kind of small sets outside of it. So if you take any part of your structure which is outside of the absorber and which is tiny, then we should be able to decompose A union this structure. So in terms of the picture, we should be able to kind of perfectly decompose this part. So of course, how do you find such an absorber is where a lot of magic is going on, and this is the hard part, and a lot of cleverness and kind of art of the absorption method. And there has been quite a lot of developments, iterations, and so on, how you can kind of build this in an iterative fashion, absorber for an absorber for an absorber, and a lot of cleverness goes into it. But for today, I'll mostly just focus on kind of this basic idea, and we'll see a few examples of how you can actually find this. So, and also very often they have some kind of, many of these results use absorbers which have some common traits, such as they're randomly chosen so that they're kind of very robustly well connected within your structure, because they need to be able to do this for any R you choose, right? So I also need to be able to decompose this. I don't let you fix an R which you want to decompose. That's kind of really the main part and the main part of the idea. But once you have an absorber, we're pretty much happy because we can use so let me again draw a picture. Or maybe let me erase this one and build a new one. So here's our structure, and suppose we have our absorber. So what we do is we go and just use our asymptotic results to decompose everything outside of the absorber up to the point where you're left with this kind of, should be tiny leftover R. And now you just use the absorption to deal with this leftover. And you get your perfect decomposition of the structure, you really decompose everything. So somehow really the key idea here, and something that you should kind of take from this, is that we took this absorber at the beginning of the argument, and we chose it very, very carefully so that it can deal with any kind of small blemishes you will have later on. And then kind of we just used our asymptotic thing, and then it could just magically kind of deal with whatever you're left with. So of course, most of the magic is here, but somehow the main gist of the absorption method or absorption ideas is this thing that you put a little bit of your structure away at the beginning, which will help you at the end. So there are this applies quite more generally than just decomposition problems, and especially the ideas. So if you know about the so-called sprinkling method in random graphs or just probability in general, this is also using this kind of idea. So specifically, you put a bit of your probability away at the beginning, and you use it to deal with kind of issues or blemishes you find at the end. So it pops up, and it's fairly useful. And in some sense, the board in the background is trying to illustrate this. So good. So that's the general picture. And I want to show you a couple of examples of how this actually works in practice. And as I said, the idea is that they should be simple. So I picked pretty much some of the simplest that I know of, which still have some kind of nice history behind them and are nice problems in their own right. So the first example is going to be in the theory of.
Why don't you push this?
The background one. Try. Works well. So it's going to be in the theory of tournaments, which are, so let me just write the definition to make sure we're on the same page, although I'm fairly sure that most of you are happy with it. So a tournament is just an orientation of a complete graph. Okay, so here's a complete graph on free vertices, and I put directions on every edge, however you want. So it's kind of depicting this round robin tournaments in which every player plays everyone else, or every team plays everyone else, and you depict with an arrow who won in every match. So they have been studied a lot, and they have some nice applications and are very fundamental objects. And in particular, one thing that people looked at a lot, and which are in some sense the most structured tournaments, are called transitive tournaments. So it is called transitive if it respects some vertex order. And again, I'm going to draw a picture. And it's gonna explain it a bit better probably. So here is a free vertex complete graph, and I put some ordering on the vertices, and then I direct all my edges to always go from a smaller to the bigger one. So this is a free vertex transitive tournament. Let me also draw a 4 vertex one. Here's 4 vertices, ordering, and you always put an edge in the direction that goes from the smaller point to the bigger point. Okay, so I'm going to be denoting them as TRN for the transitive tournament on n vertices. So one of the oldest results surrounding them is Erdos-Moser theorem, which is more of, well, what I'm going to write is more of an observation, and they mostly focused on the lower bound, which I'm not going to talk about so much. But it dates back to 1963, and it's sometimes called the oriented Ramsey's theorem. So it will also fit in nicely with the second part of the talk. But let me say what it says. So in any tournament on at least 2 to the n minus 1 vertices, there exists a transitive one on n vertices. So again, a picture, you take your favorite tournament, it can be as chaotic, as crazy as you want, and no matter how you choose it, you can always find a little bit of structure inside it. You can always find this n vertex transitive tournament. If you prefer, if you take any tournament on about n vertices, then you can always find the logarithmic size transitive one. But it's going to be a bit easier to talk in this kind of exponential way. At least I prefer.
So that looks one, the other n.
Yes, the other n is my one. Thank you. So this is a very kind of easy result. I'll show you a proof, and somehow they mostly here the main content. Well, they were doing several things with tournaments, but specifically the main content about this one is the lower bound. So they showed that you can find one of size about root 2 to the n, which doesn't have transitive n. And this is, you just take the random tournament, which makes sense. Kind of, if you want to avoid structure, taking the most chaotic one is a natural guess. But this is precisely, again, an example of what happens in Ramsey theory. I'll talk a bit more about that in the second part, that kind of we don't know root 2 plus epsilon to the n, and we don't know even a lower order term improvement here. The best that we know, as far as I'm aware, is just a constant factor improvement. So in Ramsey, we're a bit better than here. Good, so let me show you how this is proved. And it's kind of, I'll just do it in terms of a picture. So take any vertex. Everyone else is either its out neighbor or its in neighbor. So it needs to have at least 2 to the n minus 2 of either of them, of one of these. So suppose it had at least 2 to the n minus 2 out neighbors, and then just use induction inside of it. This is again a tournament, right? So by induction, you can find, or if just repeating the same argument, if you prefer that, you can find the transitive n minus 1 vertex thing inside, and then just append this vertex at the beginning of its ordering, and you get an n vertex transitive. If it happened to be here, you do the same thing, except you put it at the end of the order. So that's easy, one line observation, and has nothing to do with absorption. So where it's going to play a role is that it's going to be this asymptotic decomposition result in some sense. So the result that will have something to do with absorption is the following, and it's kind of looking at, so here this tells you can find one transitive n vertex thing, but somehow like you would like maybe to be able to find a lot of this. So it tells you that you have a little bit of structure somewhere in your tournament, but maybe you need to have a lot of it. You need to have it everywhere. And the specific thing it looks at is, well, can you decompose this whole thing into vertex disjoint transitive term? And the remarkable thing is that you can very soon after you can find even a single one, we can actually vertex partition it into and split your whole big tournament into vertex disjoint and vertex transitive things. And so let me write this as a theorem. Any n vertex tournament on n, which should be bigger or equal than some n0 of n. Well, I already said with big number of vertices can be, this is usually called a tiling. With n vertex transitive things. So of course there is an issue here that kind of if this big N is not divisible by n, you have no hope. And so we'll say that n divides n, but in general in the definition of tiling, you actually usually allow this divisibility left over. And it's equivalent which one you want to do, but let's just make our life a bit simpler. It's the same. So of course, I didn't yet tell you whose theorem it is because it was improved over the years, what we know about the n. So the first result, which tells you something here, is that you can take n to be, sorry, n0 to be double exponential in n. And this was Long and Trushinsky. (1986). Actually, this was 1985, and they were actually looking at a more general problem of decomposing hypergraphs into sunflowers or delta systems, and this is just a special case of that. So this was observed by Caro, who actually improved their general method and showed that you can actually do it already at 4 to the n in 1989. And also independently of all of this, Erdos observed the same thing. And if you kind of translate this more general approach of Caro and Long Trushinsky to what Erdos did, you get exactly the same argument and exactly the same bound. And I want to show it to you because it's like one of the earliest applications of absorption that I know of. And it's really fairly simple, and I can kind of do it in maybe 5-10 minutes, show you how it works. Okay, so let's see how this works. And then we'll do a little bit more complicated application, which is kind of illustrating maybe a few more ideas that go into building this absorber stuff. Maybe I should have kept Erdos Moser, but okay. It's easy to remember, I think. Good. So what we're trying to do is we have a big tournament and we're trying to decompose it into transitive ones, right? So this has some big, so let me write 4 to the n vertices. Good. So first step in absorption method is always find the asymptotic decomposition. And I said already that kind of Erdos Moser is going to give it to us. Why? Because, well, it tells you can find one transitive thing, but then kick it out and do the Erdos Moser on the rest, right? It still has 2 to the n vertices. You can do it, you find a new one. You keep doing that, and you keep doing that as long as you can. And then at some point you are left with something where you can no longer find it. This has size less than 2 to the n. Right, so this is in some sense small compared to the big thing, so it's asymptotic result, but it's quite a way away from really a perfect decomposition because it still has an exponential number of things which you didn't deal with. And the magic of absorption is going to let us deal with that. Good, so that we have our prerequisite. So now the first part of the argument is to build an absorber. So let me show you what it is and how you find it. It's fairly simple here. And it's just going to come from the observation that because we have a little bit more vertices, we can find bigger transitive tournaments, right? The Erdos Moser tells you can find roughly the double size transitive thing. And you can also do the same trick. You can find many of them. you can cover half of your graph with them and you'll still be able to find a new one by the same thing. So let's do that. And I'll not really need half of them. I'm going to be happy with roughly 2 to the n. Let's say I choose n times 2 to the n of these 2n minus 1 vertex transitive terms. And I want to convince you that this will work as an absorber. Okay, so this will be able to deal with, like, you will be able to decompose any kind of small set together with this thing. So let's run the absorption method. So what we're doing is we set aside this absorber A, right, which has this transitive 2n minus 1 vertex things. And then outside of the absorber, we do the asymptotic decomposition. So we take the max vertex disjoint collection of these things. And then we get some kind of leftover R. Right? And this R should have size less than 2 to the n. But let me actually be a little bit clever with hindsight and let me choose it a bit bigger than what we can get. Just somehow, you'll see in a moment why I want that. So I stop once I have exactly n times 2 to the n of them left. And I can always do it, divisibility is fine because I chose them being, like I chose them divisible by n. This is why this n exists here. All of these are divisible by n. So the total is divisible by n. So you always have these here left, something divisible by n. So I can just stop taking these things when I have exactly n times 2 to the n things left. So don't worry about it. This is just kind of a nonsense bit to make this divisibility stuff fine. It's really not the important part. Good, so let me tell you how this thing can eat up this thing. So I'm just going to, why I wanted exactly this many of them, so that I can pair every vertex here with one of these 2n minus 1 vertex. So here is this 2n minus 1 vertex thing, and I pair them up with a vertex. So this is our leftover, this is our absorber. And I claim that you can actually decompose each of these 2n vertex things into 2 transitive things on n vertices. Yeah.
Yeah, so maybe I'm missing something, but so you started with many vertices, like something which gives you one tournament of size n. Then you removed that, and then you found another one. Shouldn't that be like a tournament of smaller size?
So you mean here or
Yeah.
here? Yeah, so it's tournament of smaller size, but we're assuming it's a bit bigger than what Erdos-Moser wants. So Erdos-Moser wanted 2 to the n. Right, so as long as you have at least 2 to the n vertices left, you will be able to use Erdos-Moser on the leftover and find a new one. But please do ask questions. I mean, I'm also going maybe a bit fast, but yeah.
The matching is arbitrary, right? It will work regardless how you match.
It will work regardless how you match. So somehow tournaments are really super dense and super nice. And this is the reason why I'm showing you this picture, because a lot of the stuff you usually need to deal with, you don't here, everything is nice. And even the decomposition of how you decompose these 2n vertices is fairly easy. Well, this one needs to have at least n minus 1 out neighbors or at least n minus 1 in neighbors there. So they make a subtournament of a transitive thing. So they're transitive themselves. So you just take him and the n minus 1, that's one thing, and the remaining n vertices are the other. You got your decomposition, we won. So right, let me draw a picture. So suppose you have n minus 1 out neighbors. The in neighbors is exactly the same as we did in the Erdos-Moser, goes at the end instead. So this is a transitive thing on n minus 1. And everything else is a transitive on n. We have n vertices left. Subtournament of a transitive thing is always transitive. Yes.
How do you know that there's n minus 1?
So there are 2n minus 1 vertices in there, and it's connected to everything. It's a tournament, so it has edges everywhere. It has either in edges or out edges.
What about if everything's going in?
So okay, so no. Sorry, I'm saying like
one of them is at least n minus.
Oh, okay.
Yeah. Please. So I'm also happy with this picture,
Yeah,
right?
Okay, sorry.
No, I mean it's good. Like
Yeah, I got you. Perfect.
Don't they form together a transitive tournament of size 2n?
you don't, because these things can, like there, they can go the other way. you don't get the control right on how it looks. And you just have two transitive endings.
You can also go up on the other part. That's why you don't join to the other part, right? On the other.
Yeah. So you can have more than n-1 things here. You can also have more things going there. I pick specific n-1 things here, and because you need to, like, if you use n+1, then you cannot do the other thing. And this kind of leftover bits you need to clean up carefully here. But very good. So everyone happy with that? So that gives us, right, our decomposition of each of these 2n vertex things into transitive n vertex things. And this is it, right? We've decomposed, everything else is already decomposed. We just proved that this is an absorber. We proved the result. So it's a very nice, cute argument, I think, and it's really using the absorption idea, even though they don't call it absorption.
This is from 86, did you say?
Yeah. And even done in a bit more generality with this sunflower decomposition problem. But Erdos does really that.
So sunflower decomposition meaning that you can do a similar thing with sunflower?
Like you can decompose hypergraphs into sunflowers. That's kind of idea. I mean, there are some conditions and that's a bit more complicated. And kind of this is a nice special case of what you can somehow represent this encode the tournament says. I'm happy to send you what that is, but maybe not now, and rather show you a little bit more complicated version of how you do that. So the best result here I didn't put. So this is something we managed to do, and I'll show you now a lemma, which kind of, if you translate it back to the tournament world, you get this result. This is together with Benny, Sudakov. And it's just kind of a nice consequence of the lemma that I'm now going to tell you, and also tell you how to prove. But I'm going to tell you the lemma in the graph language because it introduces some more complexities and shows you kind of how to deal with certain problems that you don't see in tournaments because they're just super dense. So some things are really easy here. And in graph world, you kind of need to be a bit more careful. And also this lemma. Yeah.
Can I ask a question? So you mean you prove the same thing when n0 is that number?
Yeah, so it's enough to have just an n cubed factor extra from being able to find just a single one to already get a perfect type.
For both the existence of one and the decomposition, do you have lower bounds?
No, so that's a big problem. So like 2 to the n is the best we know up to a constant, but root 2 to the n is the best lower bound. That's the random graph construction. And in between, there is a little bit, but these are like root 2 plus epsilon is open, 2 minus epsilon is open. So this is kind of standard Ramsey, super hard, probably hard things.
Same thing you're stuck with.
Yeah, so here you can, I believe, you can put here like whatever the actual answer to the question is, it would work. But yeah, it's,
So, you know,
but still somehow.
you would get like whatever the right answer is instead of 2 to the n times n to the.
Yeah, you get n cubed times that, and I think a nice open problem. I think it's even true if you do 1 plus a little of 1 here. You don't need the n cubed, but somehow, I mean, how do we do it? Well, this is a little bit of a silly absorber, and it won't, like, this is why you get 4 to the n, right? You need this big thing, and you can build some kind of sparser structures which work well enough. I'm going to show you actually how that works. Well, pretty much just in a bit of a different language than tournaments. Because I want to use this lemma that I show you next to prove a Ramsey result later on. Okay, so I just wanted to mention that, and this was actually somehow like it was pointed out to us by Zachary Hunter that our lemma gives this nice thing as well. Just to convert whatever we wrote into tournament language. So thanks to him. Anyway, going back to the lemma. And so, yeah, I need to tell you what the lemma is, and now we're going to work in usual graphs. So part of the reason I'm doing it in usual graphs is also because I think maybe everyone is a bit happier thinking about graphs than tournaments. But the second reason is it's Ramsey, and it also actually generalizes, well, extends in some sense a classical theorem in graph theory called Hajnal and Szemeredi, equitable coloring. I'll tell you what it says in this language. So it says that for every graph G, let's say that it has vertex at V and edge at E, and such that the following three things hold. So I want it to have a decent number of vertices, so some 4 to the k times k cubed. And in the tournament, this would be 2 to the k times k cubed, just because I'll explain in a moment, not rush. So I want independence number to be smaller than k. This is what the parameter k is going to be. This is just the maximum number of vertices in a graph which don't span an edge.
So this 2 is an alpha.
Yes, this is an alpha. So you see, I'm writing block capitals because my handwriting is horrible, but variables and functions, I cannot force myself to switch. But I don't know capital alpha, how it looks like. Maybe it's
No, it's usually just small alpha. Right?
yeah, but yeah, I'm not doing it because of these issues. Yeah, please point out when something is really legible or illegible at all. Okay, so the third thing is that I want it to be dense. So this kind of we got for free in the tournament stuff. So in the tournament language, the conditions 2 and 3 would not exist. Here you would put 2 to the k because this 4 to the k will come from Ramsey, and there it comes from Erdos Moser, which has better number. But otherwise, the proof is kind of really line by line. Tournament is a bit simpler because some things don't pop up in what's going to happen. But I'm missing a conclusion, and that is that there exists a KK tiling of G. And once again, this is, you have your graph G, it should be reasonably dense. This is what these two things says. This says it should be big in some sense. And then you know that you can partition its vertices into cliques of size k. And once again, you have this divisibility stuff. Let me just say if k divides n, which is defined as the number of vertices. So what Ramsey's theorem tells you is that if you have, so it says that in, well, among any graph on 4 to the k vertices has an independent set or a clique of size k. I'll talk more about it in the second part of the talk, but I'm going to use it now in a moment. It's important here. So essentially, the second condition tells you that among any 4 to the k vertices of G, you have a clique of size k, right? It doesn't have an independent set of size k. So Ramsey tells you need to have a clique of size k, wherever you look of size 4 to the k. So somehow you get one of them, similarly in Erdos Moser. And once again, the claim is actually you can decompose the whole thing. And this lemma popped up while we were attacking this kind of, we realized that this is what we want somehow to solve the Ramsey problem, but it's also nice in its own right. It generalizes Hajnal and Szemeredi, which ignores the first two things and just wants a stronger condition of the minimum degree. 1 minus 1 over k would be fine here to get the KK tiling. That's the content of it. It's equivalent. It usually says something else, but this is in the complement, its equivalent version. And people looked at quite a few of these things and generalizations and so on. And in particular, Nenadov and Pehova looked at a kind of really similar problem to that. So they looked what happens if you have independence number sublinear in N. So here we're making quite a strong assumption on the independence number. They say, let's just take it to be a little bit smaller than linear. And then you can get the same conclusion, except they need semiready regularity. So the first thing they need blows up completely. And for our applications, we really need it here. So this is where your tiling 4 to the k comes from and 2 to the k comes from. So we needed it to kind of be tightened, well, tight up to Ramsey, which is this thing. And also here you can do 1/2 plus epsilon, and this is the best you can do. There is a nice construction which tells you you cannot hope to do better if you do 1/2 degree, for example. So very good. I want to show you how this is proved. So in some sense, the idea is going to be fairly similar to what we did, except we'll build a more complicated absorber. Good. And the idea which we'll use to build this absorber, I like to think of it as a local to global approach to building it, which so somehow we'll have a lot of small absorbers which can deal with specific kind of sets. Then we'll put them all together to build a big absorber which can deal with anything you want. But let me go slower and we'll see that in a moment. So the first line is this Ramsey thing that I said. So among any 4 to the k vertices, there exists a KK. Right, so this is, I'll tell you more about Ramsey's theorem. If you're not happy with it for now, just trust me that this is true. It's the Erdos Moser-like thing. I'll get back to it. So good. So the second step is what we want. So somehow this will give us our partial asymptotic result, right? Exactly the same as in Erdos-Moser. You can decompose everything up to 4 to the k vertices. And yeah, so this we'll think of as asymptotic thing. I'll not write it, we'll use it at some point. And also let me put some constants here so that it's actually true. I mean, it's true. If you were careful, you can get rid of them, but I don't want to be doing that. So I want a big constant in front. That's something like 1,000 will be fine. Okay, so then the first step of absorption is find an absorber. It's the hardest step. So let me say what we want and let me finish the argument with that. And then I'll spend the rest of the proof showing you that you actually can get what we want. So we want an A, which should be such, well, subset of the vertices, such that for any R, which lives outside of A and has size less than 4 to the k, we can decompose A union R, or well, we can tile KK tile is the language I'm using here, because decompositions usually refer to edge decompositions. And you can do similar kind of games there, it just gets harder and more complicated. So anyway, you can KK tile A union R, and again, I need for this that K divides A union R, and this will just pop up trivially from how you apply absorption, which I'm going to do now. So okay, suppose we have this kind of nice A, we have our big graph G. So you use this first line to do a partial decomposition of everything else. And you get some kind of leftover. And you know that the leftover has size less than 4 to the k, because otherwise this would tell you find a kk there. And now if we really found our absorber, which can do that, then we're done. We can just decompose this and we win. Okay? So really the main thing we want to be doing is to build this absorber, which I'm going to call a global absorber, because we're also going to have local ones now. So this says you can deal with arbitrary set of relatively big size with just this single set A, and the local absorbers, which maybe I want, sorry. So the next bit that will go into the picture is I want to build a local absorber and tell you what I mean by that. So I want for every set S of vertices, which has size K, so it's really, really tiny, I claim that there exists something which we call a local absorber, which has the following 3 properties. So the first one is that you can tile the absorber itself. You can also tile the absorber together with the set. And the third one is going to say that you can do this by avoiding a large set of vertices. I'll explain kind of from the picture why you can do that. And the main reason we want this is so that you can find many of these local things.
Avoidance means that L sub S is outside.
Yeah, so S is an arbitrary set. Yeah. So by avoiding, I'm telling you how to build this LS. Yeah, LS. By LS, well, I want to avoid this. For S is less. I mean, we will be choosing these S's as well.
Confirming that yeah. Free is LS avoiding S.
Yes.
So you mean, sorry, just to make it more clear. So you mean for any set of n/2 vertices of G.
Yeah, so I forbid you to use sum n/4 vertices, and I can still find like this thing which fixes, maybe S has something inside, maybe it doesn't matter, but I can find some LS there, which can eat up S, or it can be dealt with itself.
KK.
Yeah, K, everything throughout the thing, always KK, I'm just going to shorten it a bit, but yeah, thank you. So, yeah. So somehow these are sometimes called gadgets or switches, or depending on what you're doing, because you can deal with it itself, or you can use it to deal with this small set K. But really, this is a really much weaker thing than that thing, because each of them deals with a specific K element set, whereas this thing needs to deal with an arbitrary massive set. Yeah.
Is there a condition on the size of elements?
So I'm going to tell you how it looks like. So kind of the size will be roughly K squared. So, I mean, it depends on, this is kind of the transitive 2n-1 thing in some sense. So I'm choosing what this is, but these are kind of the conditions. So yeah, I mean, okay, I agree. Okay, when I show you what it is, I'll write the size, because indeed kind of we want for here, what the size is will tell us how many of them you can find disjointly in substance. Because we want to put a bunch of them together into this kind of big absorber, and this will allow us to clean up certain things, not actually in this arbitrary set R, but in the absorber itself. Okay, but let me show you, it's a nice construction, but yeah, so okay, so what are we trying to do? The line. So we have a set S on K vertices, and so this has K vertices, so this is tiny, so I can find a clique of size K outside. Right, among any 4 to the K vertices, I find a clique, so I can find a clique which is disjoint from S. So now we know that in our graph, so okay, let me label the vertices here from 1 up to K, let me label the vertices of the clique from 1 up to K. Now look at the 2 vertices labeled 1, and look at their common neighborhood. So everyone who is a neighbor of both of them. So remember that minimum degree in the graph is 3/4 of the total. So this one has 3/4 neighbors. This one has 3/4 neighbors. So these intersect a lot. This thing is big. This has size n/2 at least. And I'm forbidding you n/4 vertices. The whole absorber will have size roughly K squared. So I can also put that aside so that everything is disjoint from everything else. So because some of their common neighbors might be here or in the rest of the thing I'm building. So in particular, this is bigger or equal than n/4 plus say K squared plus 4 to the K. So once we forbid everything that we need to forbid, we still have enough size to find inside of this KK-1. So you can find KK, but I want KK-1 for a reason which will become clear in a moment. And we can keep doing that, right? So you do it for the vertices labeled 2, then 3 and 3, and then K and K. And in particular, at any point, I'm using at most K times K-1 plus K coming from there. So I'm never using more than K squared vertices for a single absorber. So n/4 is much bigger than whatever we have here. Cool. So this whole thing on the bottom is a local absorber, I claim. So what I need to tell you is how to tile these things. And let's do LS first. So you just take, right, this vertex has this clique in the neighborhood, so you can just tile it. And you can do that for everyone, right? Everyone has their own disjoint KK-1. So that gives you a tiling of the local absorber itself. You can also do the deal with the big thing, together with S, because you do the same thing from the other side, right? So these are in the neighborhoods of each of these vertices, but you also have this extra clique there to make sure that you can also decompose whatever the leftover there is. So we can also tile LS union S. So we have a local absorber. It's easy. It's a kind of gadgety thing. So somehow now we come to the gist, to the main part, and this is how do you build this global thing? And we're just going to use kind of these properties. So I'll show you how to do that. Yes. Okay, so now we go to building this absorber A. It's going to have 3 main parts and a bazillion of local absorbers. which are going to be cleaning up stuff for us. So the first part is, well, I'm going to call it X. It's just a subset of the vertices of our graph, which will have 2L vertices, where L should be equal to, I mean, this you choose numbers once you know what you're doing, but let me just write them. 4 to the k times k, and I'm choosing it randomly. I mean, I only want a single property from it, which will hold with high probability if you choose it at random. So let me just say what I want, and then I'll wave my hands that expectations work. And if you do union bound Chernoff, it actually works. So anyway, what I want from it is that for every vertex in the graph, its degree inside of X is at least 4 for itself. Let me rather draw a picture of that as well. So suppose you have a vertex, an arbitrary vertex. I want to find that set X such that for any actually vertex in the picture, it has a big degree inside.
Do you remind me what the V is?
V is V.
Capital V, the
The vertices of G, yeah, we can do that.
Could you just remind me how big it is relative to
4 to the k times k cubed. Yeah, so you can fit somehow, you can fit this many, like constant times L many local absorbers. That's where it comes from. Because they have size k squared, we'll see it in a moment, but that's where it comes from. And you'll see now why I wanted at least that, and this is where k and k cubed all come from. So, okay, I want that every vertex has at least 4L/3 neighbors inside of my special set X. Why it makes sense that the random will do that? Well, remember that minimum degree was 3/4 n when we started. So you expect that it should have 3/4 of the size of X, which is 3/2 L. And then I cut us a little bit of slack so that the Chernoff is strong enough that you can do a union bound, and this works with high probability. And then I fix one and forget it's not really random, it just comes from random. And this is in some sense really what will, just this X will be our absorber in some sense. The problem is that when we use it to deal with R, we are going to make a mess on X. And then to deal with the mess on X, we are going to use the local absorbers. So we're going to add up some local absorbers, which will let us clean up what's going on X. Okay, so let me actually show you this step. So let me show you that I can eat up everything in an arbitrary set of 4 to the k vertices by using just this set X and this property. And then, I mean, it's not the correct way of saying it because you need to first build the absorber, but just somehow this is the only place where we'll use this. So let's deal with that and then let's look at the other stuff. So we have our set X and we have our set R, which will have size less than 4 to the k. So because everyone has a big degree inside of X, you can find, right, this is at least 4L/3. So you can find inside, this is at least 4 to the k. So you can find the kk-1 there. And you can take this vertex, this kk-1 in its neighborhood. It deals with this vertex and the chunk of X. And you keep doing that, right? So in total, at the last step here, we used up at most k times 4 to the k vertices from X, right? Because for each of them, we use k-1 things here. So there is 4 to the k of them. So in total, we always have, like, we never use more than k times 4 to the k things from inside here. So you always have at least, you have at least L of them left here. And at least half of X. This is how I chose this to be 2L, and this is 4 to the k times k. So you can decompose the whole of R together with a chunk of X. And this was easy. This is simple. We didn't do anything terribly clever yet. So, and also note that at any point we're using at most L vertices of X. So everyone still has L/3 neighbors, which are free. So we can really find these things repeatedly. Good. So that means that we can decompose everything up to R union some X prime, say such that X prime has size, well, it's a subset of X and it has size less or equal than L. And I can actually make it equal to L by just the standard tricks that we've been doing. And I'm not sure where I should go. But okay, we're kind of not gonna need this. I'll write it again. So why? Because so far we've used up a chunk of X, which left us with at least L vertices. So we can just, this is big still, right? So we can find KKs. You can find vertex disjoint KKs until you're left with precisely L things here. So this, you need divisibility to work out. It will work out, don't worry about it. But the main thing is just I want to be able to write this equality. We'll get back to how, so now the only thing you need to do is we need to decompose this, like the X without X prime prime, together with whatever will be my leftover of the absorber. And what we achieved, and what is really the kind of the clever thing here, is that we now need to look at only a specific set. So before this R was arbitrary, you need to look everywhere, but now we only need to fix a single set which we chose at the beginning, which is much, much easier, and which is why just a linear number in some sense of these local absorbers is going to be fine. We can find the size of this many local absorbers. We cannot find how many different subsets of R you have, or different R subsets you can have. So this is kind of a first step in the iterative absorption thing. You are somehow focusing your problem on a specific smallish set. Very roughly speaking, not there are quite a few extra things that you do there, and it's focusing on different things. But okay, let's go on with the construction of our absorber. So far we just took this, and everything that I did below it was just properties, like what you can do with just this set X. Now the two next main things are kind of more, you can choose them however you want, they just should have some kind of sizes restricted. So Y should be the subset of vertices without X, it should be disjoint from it, and it should have size 2L, sorry. And Z should be disjoint from X and Y. And it should be such that it should be a vertex disjoint union of something which I call blobs. And these are just sets of K-1 vertices. Let me draw a picture rather than that. So here's X, it has 2L vertices. Here's Y, it has 2L vertices. Here's Z, it will actually have 3L times K-1 vertices, which we partition into blobs of size K-1. We'll see in a moment, this sounds a little bit strange why we want that, but somehow the idea is that our local absorbers deal with sets of size K. Right? So we want to be able to deal with one vertex from the left and one blob on the right. So that's why we do it in this strange way. But so far, what's happening between Z and Y in terms of edges of our graph, I'm saying nothing. You can choose them to be whatever you want. Everything is going to be fixed by the local absorbers that I'm going to add now. Okay, so now let me tell you what we actually choose for the local absorbers. So now for every vertex which lives on the left in this picture, so in X union Y, pick 40 blobs and call pairs BBI good. Okay, so every vertex there is going to choose, so let me take a vertex there, he's going to choose some 40 blobs here. And I'm going to tell you it's important how we choose it, but I'm going to tell you in a moment. I want to finish the construction first. But ultimately, doesn't mean there are edges here. I just mean this is a good pair. This is an edge in an auxiliary graph, if you prefer. It's just some kind of good pair for us. So in total, we have 160 L good pairs. because you have 4L vertices on the left, each chooses 40. So for each of them, I'll choose a local absorber, right? Each pair is just a kind of a set of K vertices, one here, K minus one there, and put a local absorber inside. So for every good pair, VBI, put LS, where S is V union BI, into A, and do it disjointly.
That's what you're gonna avoid.
So the picture is, this is our, so far our absorber. So what we do is we just put kind of 160L local absorbers, which allow us to deal with any good pair.
And you can pick them because you.
So this is 4 to the K times K, right? Because we can avoid a linear number of vertices. This is 4K to the K. Each of them has size about K squared. So in total, this will be less than N over 4 vertices at any point. So we can always avoid them when we find a new one. Okay, so very good. So this is our absorber. This is our massive big A. And I need to tell you what property I want from these good pairs. So what I want is that for every X prime, which is a subset of X and has size exactly half of X, size of X prime is equal to L, there exists a matching of good pairs. Mx prime, say, of good pairs. And let me go into the picture again. So if I forbid you some arbitrary set of L vertices here, which is going to come from this thing that I showed you here, right? This is what we use up to deal with R. I want to be able to find a matching between everything that's left here together with Y and the right-hand side thing, right? So matching of these good pairs. Yes. So you need to be a little bit careful to avoid that really kind of computation-wise. So the construction here is Richard Montgomery's so-called graphs, which are resilient for matchings. You need to be a little bit careful with calculations, but you're perfectly right. So you just drop kind of 20 random matchings, but you do it between Y and a subset of Z, and then you do some copy vertices, you do Hol's matching. It works out. I don't want to go into that. I'm happy to tell you more how it works or during lunch or at any point. But it's just a probabilistic calculation. And as you said, it's correct, but this is one of the results here in the background. And this kind of robust matching construction, this is maybe 4 or 5 years old now, and it has found quite a few applications. It's it lets you build this kind of nice things, because why? Let me finish now. Assuming that we have that, well, we already decomposed this and our arbitrary set R. That's what happened there. Yes, there. So now for each of these pairs in the matching, use their absorber to decompose the set together with the local absorber, right? That's the property that we have of local absorbers. They can deal with your small set and itself together. So that will use up 3L of your local absorbers. It's going to deal with everything that's left in this picture. So X prime, which is this kind of leftover, Y and Z. And we then just have a bunch of local absorbers left. And for that, just use the fact that you can decompose them on its own. We're done. So that's the whole proof. And somehow really the key idea was this, that you focus on this small place, and you can keep doing that in some sense when you're dealing with more complicated structures where the picture is not so clean and perfect. And if you keep doing that multiple times, it gets more and more complicated, but you can build quite a lot on this idea. And I think it's kind of nice and fits roughly. So let's have maybe, yeah.
I could ask at the break if you want.
Ask.
So I'm confused about the order of things.
Yeah.
I get each of these two pieces, like how the Z, is that just the fact that you can come up with the Z like that?
So Z, I just choose it to be disjoint from everything else. I'm just choosing 3L times K minus 1. They can be whatever you want. they are dealt with by choosing later the absorbers for them.
But the fact that you can decompose it into the K-1.
So these are not cliques. These are just K-1 arbitrary. Sorry, I should have said. This is not a K-1. This is just an arbitrary set of 3 elements. Yeah, because remember here, I didn't care that S was a clique.
Sorry, so R came from what? I forget.
So R is an arbitrary set. This is what the absorption does, right? You take, so the whole argument, I did the first part sometimes ago. Yeah, so the full argument goes in the proper order. You build this structure, forget about anything about R or whatever. I take my X with that property, I take some random, whatever, not random, but whatever, arbitrary Y, arbitrary Z. Then I choose these pairs using the random construction or however you want. For each of them, I put a local absorber inside.
We have enough, I have to work out the calculus. We have enough stuff.
You have enough space and this avoiding thing is going to be good enough. Size is perfectly cool. And then after that, you decompose everything else using cliques. You're left with some R. You use R, you'll get this kind of leftover thingy at the end. And because you pick this in this resilient way, we'll be able to find the matching no matter what this thing will be. And then you decompose that plus the local absorbers. So that's the whole structure. I just kind of went maybe in a bit strange way because it seemed more intuitive to me, kind of like one step after another. But yeah, good. So let's maybe have a, I don't know, couple of minutes break.
5 minutes.
And then we switch gears and I'll show you how, well, lemma is no longer on the board, but how to use it to prove an old question, Ramsey theorem, and where it all came from. Thank you.
Right. Did the organized large font? That's very beautiful.
Yeah, I really like the argument, and I really like that. I mean, it fits in 2 hours. I can never say it.
No,
usually
but
because-
you also explain what was it.
Presentation, and I love it.
Yeah.
So I guess we'll get to this, but like, is there a meta theorem that kind of like, a couple of meta theorems? Because it seems like
that's-
there's like, what, I don't know how to say this, but like,
So, I mean, yeah, so this kind of, I mean, it popped up in this is what we needed to prove something. So that will now come up. But yeah, I mean, it's also many of these results. I think this is a thing that's a bit sad missing, that somehow a big hammer
Yeah.
for the
I
absorption.
mean, I've seen
method.
absorption used in bit more baby ways, you know, like with in additive combinatorics.
So I would,
But I haven't seen like this sophisticated, it makes me wonder just how many more
so
things.
this is
So cool.
this is not even really
Yeah, this is
as far
easy,
as it
yeah.
goes.
I figured.
I mean, some of these are
I follow it,
100-page things which are really, really carefully tracking things and building on top. This is just kind of one step of what you're doing.
And all those
And it's kind of-
references, they're applications of absorption.
So most of them are applications of absorption, or at least they use absorption ideas. Like Peter doesn't like, so this is maybe the biggest, one of the really, this existence of designs on the left, one of the top results in
Which one?
extremal
Which is the one?
existence of designs 2000 on the left. I should have, but he doesn't like to call it absorption method because it's kind of not. Like he's using absorption ideas and he's building some kind of semi-algebraic random construction.
This is not to prove. So far you've been going from the existence of one thing to a tiling. This is of a different. This is
Yes, it's a different. So yeah, and yeah, they did a different proof, and they are using really iterative absorption. So they are using more things.
Are you going to go over this stuff? And are you?
Not really. So now I'm switching gears. So kind of it's a bit.
Can't do too much.
Yeah. So I think.
I mean, this will take.
No, I meant like not, you know, just a quick summary. It's okay. It's.
Yeah, I mean, I think even quick summary of many of these things.
That was.
Yeah, I mean,
Summary, I get you. So good.
So
Yeah.
does this imply anything for the tournament chromatic number stuff that people study, like related to like Erdos? Have you ever seen that?
I've seen that. I don't.
I don't know if
but not.
Yeah, well, I know very vaguely.
So this.
Useful to use tournaments and talk about tournament number, which is essentially about
Happy to look but I don't. I mean, there is a few things like this. I said Nenadov and
Sorry for causing you to waste your time yesterday.
It's kind of there is a lot of things that more Ramsey to run.
Wow.
Not seeing tournaments much, but I mean, it is kind of like if you do this approach in tournaments, you will get and this is precisely, but I think somehow there, like the tournament, at least the chromatic number is this cyclic number
or whatever, and that the other
so
just
so
No, but I mean,
you say that the graph, like you don't have independent sets. The equivalent notion is that you have an acyclic cycle. So set with no cycles.
You do require it to be.
But it's not a tournament, sorry. So that would be transitive. But in general, you're at the graph, it's a cyclic graph.
No, I mean,
But actually, now that you're saying it, that's precisely what
simulation itself.
We can look. I didn't.
I was just wondering if you
Realize, you know,
It looks very similar.
like those two things are pretty important. And then it would find that.
Maybe I'm very happy to talk about
There's also, that is also very well studied.
Yeah, it's true.
but I feel like
Well,
I'm agreeing with.
Okay, so let me erase the boards.
זה לא בדיוק, יש, זה לא, זה לא,
It was that hard.
זה לא, אבל גדול מה, אתה מקבל פקס או לא סוגר, זה מה שאני
Notes would help him a little bit with running the simulation that he could have done by himself without any neural networks.
Okay,
אוקיי.
so second part of the talk. So if you've lost me or you didn't like the first part, now's a chance for redemption. And well, for you to come back in, because somehow there will be some similarities and we want to use this lemma that I showed you in an actual proof. But other than that, kind of, this will be of a very different flavor in some sense. It's a different area and different kind of things. So again, the idea is to give you a bit of a picture of what people look at, or well, specifically this problem that I want to tell you about. So what is Ramsey theory? It refers to large body of results, which all roughly speaking say that in any sufficiently large structure, you can find a well-organized substructure. In other words, I like to think of it as saying there is complete chaos is impossible, despite all evidence to the contrary. So we've seen Erdos-Moser, that's precisely the kind of thing that it looks at. It told you you cannot have a completely chaotic tournament. So its origin is Ramsey, like it's Ramsey's theorem from 1929, which says that in any, that for every graph H, there exists a least positive integer n, which we call the Ramsey number of this graph H, such that in any two-edge coloring of a complete graph on this many vertices, there is a monochromatic copy of H. And MC is my shorthand for monochromatic because it's a long word. So maybe you're more familiar with this, and the version I used is when H is a clique. That's kind of the most classical example. And then also, if you don't like the coloring version, it just says that if you take any large enough graph and large enough for a clique, the best we know is 4 to the k, 4 to the n, or however many vertices you're having clique, then you can find a clique of size k or an independent set of size k. And this is a generalization. So the two-edge coloring means I think of edges as blue and non-edges as red, but I'm doing it because it will make it easier for me to draw a picture because non-edges are hard to draw. So that's the idea, and it says this for any graph H, and these kind of Ramsey numbers have been studied a lot. We have a lot of results, but let me just tell you what we know in the clique case. So this is already something that I mentioned. So we know that it's at most 4 to the k and at least root to the k. And here we have some amazing results which improve both lower and upper bounds, but only in lower order terms. So 4 minus epsilon is a massive open problem. Root 2 plus epsilon is a massive open problem. And these bounds are, this is from 1935, Erdos and Sekeres. This is 1947, Erdos, one of the first applications of this probabilistic method, taking the random graph. So the reason I'm saying it, besides that I use this result already and I'll use it again, is that figuring out Ramsey numbers is hard. It's a really big, hard problem. We very often don't know what to do with it. So it comes as no surprise that we know Ramsey numbers only for very, very few classes of graphs. We know it for quite a few specific small graphs, but if you want some kind of growing family, there are really, really very few. So we know Ramsey number of H for H when it's a pot. And this only because I'm talking about 2 colors. If you go to 3 colors, again, we don't know. So we know it for a pattern cycle. These are all both classical results, 1960s. But there is a third class of graphs, which is perhaps a bit less known, but in some sense, it's way more general than either of these. These are these called copy graphs that I'm going to talk about today. So what's a copy graph? Pick your favorite graph, whatever it is, absolutely arbitrary, and now take many, many vertex disjoint copies of it. Okay, this is a copy graph. This I call a copy graph at least. So you need to take a big enough size for this node to start to kick in. I'll tell you a theorem of Burr, Erdos, Spencer, which kind of covers this thing. But let me just also introduce notation and by what I mean by that. So a copy graph is just, I'm going to be denoting it as n times h, and this is n vertex disjoint copies of H. Let me draw a picture. H is, let's say, a triangle, then 3 times H is just 3 vertex disjoint triangles, a 9 vertex graph. So now take, also if you, I don't know, add an edge, then just in the copy you add an edge for everyone. So these are, I like to call them copy graphs, and yeah, very good. So as I said, this is quite a general class. You can start with whatever graph you want, but obviously this no cannot be true if I allow you to do n equals 1, because then this story about them being hard and we don't know would be we would know it for every graph and we don't. So what I mean is that you need to take many, many copies, and this is, yes, keep forgetting that. Oops. I didn't break anything. Some exercise as well. Good. So let me write the theorem, which kind of covers this case and can remove the quotation marks. So it's due to Burr, Erdos, and Spencer from 1975. And it says the following. So let H be a graph without isolated vertices. So this is some kind of nonsense condition to make the statement true. But in reality, if you know Ramsey number for a graph without isolated vertices, you can also figure out the rest. So I'm just putting it inside to make it correct. So let H be a graph without isolated vertices. And then there exists an n0, which should depend on H. So this is the number of copies you need to take for the Ramsey to kick in. And we need a constant, which is going to be the free term in some sense, also depending on the graph, such that if you take, so this for every n, which is at least n0, the Ramsey number of n times H is equal to twice the number of vertices in H minus its independence number times n plus c. So somehow, given how hard these things usually are, finding a result which tells you something with equality in Ramsey theory is really, really surprising. And it's a really nice result. Of course, why the no has quotation marks is because I didn't tell you what C is and whether we know it. I'll get back to that. I want to show you a proof of this. And that will show up kind of what's going on with this N0 and C. And it's a kind of mishmash of the original proof of Burr, Erdos, Spencer, of what Burr did and what we did. So, but it's nice, should fit and illustrate a little bit how I actually break the board.
Survived for 100 years.
Well, it didn't survive Ramsey theory, apparently. Okay, so I want to show you a proof of this result for various reasons, but also because it will illustrate what we'll do later. And it's kind of the analog of this, what we did with, well, anyway, I'm not finished that stage.
I did, yeah, I did.
Good, so proof. So first, let me show a lower bound, which is not going to be correct, not perfect, but it's going to be good enough so that we can use it at 2 more times in the proof, and it will give us, it will be an important step in the full proof. So how do you prove a lower bound for Ramsey numbers? You need to give me a big complete graph, a coloring of it, which has no monochromatic copy of, in this case, NH, right? So that's our task. So we'll have our complete graph is going to have 2 parts. One of them I'm going to call blue part, one of them I'm going to call red part. Blue part is going to be completely blue. Every edge inside of this is colored blue. The red part is going to be completely red, not too surprising. And I'm also going to color every edge in between red. Now, I also need to pick the sizes. So here I'll choose it to have nk minus 1 vertices, where k is the number of vertices of our H. And also alpha will be the shorthand for the independence number of H. So what I do here, and these numbers, don't worry about them for now. It's going to be clear in a moment why I'm picking them this way. Here I put n times k minus alpha minus 1. So if you add up the number of vertices, you get 2k minus alpha times n minus 2. So if this doesn't have a monochromatic NH, we get the lower bound of that form with C being minus 1. Okay, and it's minus 1 because Ramsey is defined as the smallest where you can actually find it, and I'm showing you an example where you can't. Okay, don't worry about this plus minus 1 too much. So let me show you why this has no monochromatic NH. So first, any blue H, I claim needs to live inside of the blue part. And why is that? Well, we assumed it has no isolated vertices. If it had a vertex in the red part, it would not have any blue edges. So in the blue graph, it would be isolated. But that means it needs to fit completely inside. So if you could find n vertex disjoint copies of them, they would all need to be here, and they don't fit. This is why we put nk minus 1. And this tells you you have no blue NH. Very good. And we can play a similar game with red. So any red G is not going to be completely inside the red part, but it will have at least k minus alpha vertices inside the red part. Why? Well, suppose you found a red G, then this blue bit is an independent set in the
Was it GH?
H.
H, yes, sorry. I'll have later 2 graphs. Red is G, usually blue is H. Yeah, thank you. Any red H has at least k minus alpha vertices inside of the red part, because in the blue part, it's an independent set, right? So it has size at most alpha of H, the maximum independent set. So that means you need to put k minus alpha of them here. And now if you could find a monochromatic red NH, then each of them has k minus alpha vertices here. So once again, they don't fit, right? We choose this number specifically so that they don't fit. So we know there is no red NH. And these 2 things together tell us the lower bound of the Ramsey number. So that the Ramsey of NH is at least 2k minus alpha times n minus 1. And let me call this inequality star, because it's going to pop up. So it tells us that the Ramsey number is at least big, and then we can make it big because we can choose n to be big, right? In the theorem, we're saying that I can choose n to be bigger than whatever I want, depending on the graph. So let's now go with the proof, and I need to push this up. True, actually. Yeah, but for some reason, I'm not using.
It's good for the exercise.
That's true. I definitely need it. So. Good. So, okay, so now let's actually prove the result that I just erased. So, very good. So let chi be an extremal coloring. So by that I mean be two coloring of Kn, with n being Ramsey number of nh minus 1 without monochromatic nh. Okay, so I'm just taking an extremal coloring. It exists by the definition of Ramsey. And my goal now is going to be to understand how this coloring needs to look like. And from that, get a bound on the Ramsey number itself. So that's what we do now. So now we'll use the trick that we've been using a bit in the first part of the talk as well. And that's going to be to take a maximal vertex disjoint collection of blue copies of H. This you can think of as this kind of, in some sense, this asymptotic part, if you want. But anyway, we have, so what do we know about it? We know that it has at most n times k vertices, because if we found n of them, then we are done, right? We're assuming there is no monochromatic nh, so you cannot find more than n minus 1 of them. So I even have a bit better bound, but I'm being wasteful. Okay, so you cannot have more than n blue H. Each has k vertices. At most, nk vertices are in this maximal blue vertex disjoint collection. So what do I know about the rest? I know that it has no blue H. And I know that it has still at least n, capital N minus nk vertices. Right, this is how many I use there. This is how many I have in total. So let's use our inequality star. And what you get is that this is at least k minus alpha times n minus 2. Why? Because n is at least, by that inequality, 2k minus alpha times n minus 2. We have another minus 1 here and 1 minus 1 there. So this eats up 1k. You're left with k minus alpha. So you get this number. Okay, so why I'm doing all of this is because I claim that this is still big, because this needs to be at least 1, because if alpha is equal to k, then independence number is equal to the number of vertices, the graph is empty. And we're assuming it's no isolated vertices, don't worry about it, it's at least 1. I really just want that this is at least something that depends on n, and because I can assume n to be big, and then I can do stuff there. Okay, so now, suppose n is at least Ramsey number of H versus a massive red clique. So what is this? This is the minimum number of vertices you need to guarantee a blue H or a red K clique of size K to the 2K. If you wish, I can put here K, 2K, or just Ramsey of K2 to the K. It will contain this, and it just depends on H, which is the thing I care about here. But then you would get double exponential. You can get a bit better here. Doesn't matter at all. We'll see better things in that direction later. But so far, I can take my n to be as big as I want just by choosing n0 to be big. And let me put this 2 here to get rid of the blue thing. So now this thing has size at least Ramsey of H versus K2 to the K. So you can find a massive red clique inside of here. Right? So, and there was nothing special about blue. So we have a red K2 to the K, and I claim we also have a blue one, because you can do the same thing with colors reversed. You can take a maximal red thing and do the same game. Okay, so the picture now is a red big K to the K and the blue one. And now look at the majority color of the edges in between them. It has density 1/2. So you can use Kováry-Sors-Turan theorem to find a complete bipartite graph in one color in between them. So let me just draw what I find, and I can tell you also another argument which doesn't use Kováry-Sors-Turan if you don't know it. But the claim is that if red was majority color, then I can find this kind of 2K vertices, K left, K right, so all the edges in between are also red. This happens just because you have constant density in between. If you check what Kováry-Sors-Turan tells you, you get it. But also if you prefer, just take 4 to the K times K sized cliques. So take a bit bigger N, it doesn't matter, it's still double exponential. And then you can do a greedy argument to find this. You just take a vertex on the left, you keep its majority edges, delete everyone else, do another one. If you do it 2K times, that will eat up your 4 to the K and still leave you with K vertices there. And then pick whatever color appeared more often there. And K of them will be at least, so that gives you this kind of thing. So it's not a hard thing, but it comes from Kováry-Sors-Turan, and I can find that fairly easily. Good. So now, okay. It's really in the middle of the board. All right. Okay. So far we found these things are called joins. So this is red clique, all red in between, say, maybe it was blue, it doesn't really matter for us, and this was blue. And let me sacrifice a few vertices from the left and choose K minus alpha of them here and K here. So what I want from them, so this is again in this absorption making divisibility work in some sense equivalently. But anyway, so the property that I want for this is it has 2K minus alpha vertices and it has H in both colors. And this is kind of penultimate line of the proof, and it's fairly non-clear where I'm going at.
But there exists.
Almost penultimate. H in both colors. So you can find the blue H, that's trivial, you have a clique of size K, but you can also find the red H because you put the maximum independent sets there and everything else here. Okay? And we found this on a very, very few vertices. So let me draw a picture, what we have so far. So we have 2K minus alpha vertices, which have this property. And in total, we have Ramsey of NH minus 1 vertices. You also know that in this remainder, there is no monochromatic n minus 1 times H. Right? If you could find it, then you can use the appropriate color one from here to extend it into a monochromatic NH. And that brings you back to, that would give us a monochromatic NH, and we're assuming that we don't have it. Good. So that gives you a bound on the size of this leftover of Ramsey of n minus 1 times H minus 1, which gives us a recursive upper bound on the Ramsey. So what did we show? We showed that the Ramsey of NH minus 1 is at most 2K minus alpha, these special vertices, plus the Ramsey of n minus 1 times H minus 1. So let's get rid of the minus 1s. And let's write this in a nicer way. So I claim this tells you that the function f of n, which is Ramsey of nh, minus n times 2k minus alpha, is decreasing, not necessarily strictly. Why? Because take out this thing from both sides, n times 2k minus alpha, you get precisely f of n on the left. And here, one of them will get eaten up, so you get n minus 1 of them, so you get f of n minus 1. But what else do we know about this function? We know that it's bounded from below by -1, this is our inequality star that I erased from somewhere around here. It said precisely this, this minus this. Well, it said this is at least this minus 1. And what do we know about the function which is decreasing and bounded from below? It eventually stabilizes, it becomes constant, which is precisely what Erdos's theorem tells us. If you take n big enough, it will become constant. So it's a nice proof. It's a bit of an unusual Ramsey proof in some sense. You don't usually go around it doing it that way. And they already pointed out two major drawbacks, though, which I kind of talked a little bit about as well, which is that it tells you absolutely nothing about how many copies you need. So remember, we had this assumption, you needed at least that, but here we're using that the decreasing function, non-strictly decreasing function stabilizes. This, we have no control when it happens. It can happen.
It's non-strict.
Yeah, precisely. And yeah, so, and you know that it will become constant eventually, so it cannot even be strict really all the time.
No, if it was strict, you would know roughly how much n you can.
Sure. So, I mean, it's probably strict and then it becomes constant. And I even, like, if you can prove it's convex, even better for, but anyway, I have some stuff that would be nice if you can do that. But anyway, I don't know that. So they pointed out one major problem that you'd have no control on n, and it also you have pretty much no control on what the constant is. And I said that we know the Ramsey number, so I was maybe slightly paraphrasing. So anyway, they pointed out two, not paraphrasing, but well, you'll see in a moment that there is a somewhat better justification for what I wrote than just this theorem. But they raised two questions to kind of deal with both these two drawbacks. The first one is, like, what is n0? When does this long-term behavior kicks in? Give some kind of bound, or at least, or understand it in some sense. The second question, and both of them are actually Burr, Erdos, and Spencer, I'll not write it, 1975, find C of H, or what is C of H. And following this nice theorem, a nice result, there has been a lot of work which kind of answered this question for specific graphs, trees, cycles, forests, and there is quite a long list of papers, and figured out what these two factors should be. But so let me just mention one of them, which is kind of nicest and which actually was done already by Burr, Erdos, and Spencer themselves. So they proved that if you take n copies of a triangle, it's equal to 5n if n is at least 2. So if it's 1, then it's 6. So it's n0 is equal to 2. It's a nice kind of result, but there is a lot of them. But for today, I want to focus on general results. And here, the strongest result is due to Burr from 1988. It's actually a series of 3 papers doing various things related to this, but somehow the two things relevant for us are that he gives a bound on n0 of h. So he shows that it's at most triple exponential in, did I write the correct? Yes, size of h. Thank you. And he gives a finite but implicit way of computing C of h. Somehow, okay. So what I mean by that is that he can show how some extremal coloring looks like, from which it's a finite computation to figure out what the actual ultimate thing will be, but it's pretty messy. He gives two, one lower bound, one upper bound, neither of which is always tight. And even these are a bit messy, but so far, I think for most of these examples, they tell you either one or the other is true. We do a bit of a better thing. We have only 3 different weird functions there, but still it's an open question of Burr to find kind of an explicit, nice characterization of what this C of H is, but at least it kind of, in some sense, tells you that we know what C of H is, or at least could compute it, although I know. Okay. So that's what Burr did. And let me tell you, so I don't want to tell you how this actually works because it's a bit messy, it's a bit complicated. So let me rather tell you a corollary that he got. So if n is where the numbers are somewhat nice, if n is at least this triple exponential in k, then the Ramsey number of n copies of a clique is equal to 2k minus 1 times n. And this is what it should be, right? Because it's twice the number of vertices minus the independence number, which is 1 for a clique. And the constant here is Ramsey of kk minus 1 minus 2. So this comes up from his upper and lower bound. And it also tells you in some sense that you cannot hope here to get better than an exponential bound, because if n was sub-exponential here, then this is the main term. We don't know the Ramsey numbers, but they grow exponentially, that we know. So this would be the main term. So you might not be able to find even a single kk on this many vertices, let alone n of them. So you cannot hope to get in general here better than the exponential thing. And our main result is that you can always do exponential. So we improve this triple exponential to just the exponential, which is the best up to the constant that you can hope for. This is theorem, and all of this is with Benny. That's n0 of h is at most 2 to the big O of h, and even the constant is not too horrible. Good. So now this, because of this, so we have a little bit better characterization of C of h, but it's still a bit messy, and I don't want to go into that. And instead, I want to show you how to prove another theorem, which uses kind of the same set of ideas. You need to add a few things to get to this one, but the other one should fit in maybe the remaining 20 minutes or so. And
Can I ask a dumb question? That corollary, is that really if n is bigger than or equal to n0 of h?
n is bigger.
I mean, like, does your theorem say that the corollary holds?
So yeah, our theorem will allow you to do 2 to the, I think 10k is plenty for 2 to the 10k. I didn't actually check it any, but like it's a bit easier for cliques than general graphs. So somehow cliques are nice and easy here, but well, easier. You still need to do a lot of the work. But somehow sparser graphs cause some trouble. But anyway, thank you for the question. So as I said, I want to tell you another theorem, which both of these Burr, Erdos, Spencer, and Burr paper also raised. It was an intermediate result for them, which let them prove this thing. We don't use it as an intermediate thing. We kind of just use the same argument to prove, well, similar argument to prove both things, except this one is a bit more messy because you don't have a nice answer for what the number is. And it's in some sense an asymmetric version of this theorem. So we put what the Ramsey number of a single graph versus a big copy graph is. So let me show you what that is and show you a proof, which will finally bring us back to this lemma that I showed you at the end of the first part of the talk.
So this will replace the Ramsey number of h and a big clique. You'll use the Ramsey number of h and nh.
Yeah, so I'll do G and NH because now they play different roles in colors. So to kind of indicate this is where the G thing came from. So I'll write the theorem. So and again, we need this kind of nonsense assumptions. So let G be non-empty. And again, all of these things are usually easy to get rid of. It's just here to make the number that I write correct, and usually for the lower bound. So G is non-empty, H connected, and K be the maximum of their sizes, but feel free to think of G equals to H. This is kind of the main content. I just want to have two different graphs because now this will be red, this will be blue, and they play different roles in the colors. It's not symmetric.
Just for some high-level intuition, you have 3 exponentials and you want to reduce it to 1, so you have to reduce 2 exponentials. One, I guess you're going to do through this Ramsey bound, replacing clique 2 to the k by nh.
So,
and the other is removing the Kovalychuk-Storan argument, because there you also lose an exponential.
You also lose an exponential, but so in some sense, yes, you need to be careful there. But in some sense, you don't need the main idea is that you don't need complete things. And this is also where that lemma comes in, right? That's told you that if you have a dense blue thing, then you can still tile it. You can still completely split it into these kind of graphs. So it will come into, but this is kind of the main thing. You don't need complete things in your picture.
To get many H's.
Yeah.
Yeah.
So-
Okay, good.
Yeah. It will come up here. I mean, here they had a double exponential upper bound here, and they accumulated another one, which when you use it for the final thing, but we need just something n being at least 7k, then Ramsey number of G versus NH is equal to n times the number of vertices of H plus the Ramsey number of a certain family defined by G, which I'm going to explain in a moment, against H minus 1. And this family is like Burr defined these 4 different types of this family, and they are what goes into this bound. But this is the symbol, one of them, and let me tell you what it is. It's not too complicated. It's just if I wrote 4 of them, it would be too complicated, probably, and needless. So G prime, so it's a family of subsets of G, which you obtain by deleting an independent set. I'll explain. So you take your graph G, you find an independent set there, you delete its vertices, whatever you're left with, you put in the family. That's a subgraph, right? It has less vertices, you just put it there. You do this for every independent set in your graph, and you get a family of graphs. So for example, if you take a clique, then every independent set is a single vertex thing. So this will just be a kk minus 1, which is also where kind of that kk minus 1 comes into that result. So, and I should also say that the Ramsey number of a family versus H is the smallest number of vertices, which guarantees you a red member of the family or a blue H. It's a standard extension of the usual Ramsey definition. Good, so I want to show you how this works. And first, let me show you a lower bound, which kind of shows where all these numbers come from. And also because once, I mean, we'll not use it we'll use it a bit, but we'll not use it much as before. It's more, we're going to try to push an extremal coloring to look like this extremal one and then get some understanding from that in some sense. But okay, yeah. I should practice with these boards. Every day, 1 hour boards going instead of gym. Sounds good.
And the problem is that after every time you do that, you get free lunch.
Yeah. Well, proof, lower bound. So again, I need to give you a construction. It's going to be similar as what we looked before. It still has a big blue set, but now it will not have a red set. It will have, we'll call it C, because it is going to use some blue edges, but it's going to also use some red edges. But in between, I'm still keeping everything red. And the sizes I'll take are going to be, so on the left, it's n times the number of vertices of H minus 1. On the right, sorry. And here it's Ramsey number of this weird family versus H minus 1, so that I can color these things so that there is no blue H and no red G prime in this family. Right, so this is again a definition of this Ramsey number. And this is precisely what we want, right? This is 1 less than what we claim the Ramsey number is. So if I can show this has no red G and no blue NH, we have a lower bound at least. So let's see why that's true. So I claim that still any blue H needs to live inside of the blue part, because now we're assuming that it's connected, so it cannot be split between the parts. We assume there is no blue copies here, so all blue copies go there. Once again, they don't fit. Okay? So this means no blue H. Now what about the red G? So suppose that we found the red G. Observe that in the blue part, we found an independent set. So if you delete this independent set, you get a G prime, which belonged in our family in red. So this is not possible. There is no red G. And this gives us that the Ramsey number of G versus NH is at least this n times H plus the Ramsey number of this strange family versus H minus 1. And let me call this whole number capital N because we're now going to use it for this signal. Okay, so now we have the final bit. So that's where we finally use this lemma. So we want to prove an upper bound. So let's once again chi be a coloring of, it's a two-edge coloring, it's always a two-edge coloring of Kn without red G or blue H. Okay. NH, yes, thank you. So I'm here actually going towards a contradiction, right? Because I'm saying I want my Ramsey number to equal that. So I actually want to guarantee that you can always find one of these things in these many vertices. So I'll get a contradiction at some point here, but it's similar kind of idea as before. Good. So what do we do? So where do I go for that? Okay. So the first thing we do is similar to what we've been doing before. So it's like we want to find a massive blue clique. Sorry, I just got a bit momentarily lost. So I want to somehow find structure which looks similar like this extremal coloring. So what I want to do is I want to find a blue massive clique. That would be ideal. Finding blue cliques of this size is impossible. There is no chance you can do that with what we know so far and even in general. So what we'll do instead is we're going to find a set which is predominantly blue. So it's really most of its edges are blue. And by predominantly, I can now tell you that it's pretty much, it has these conditions from the lemma. It has big minimum blue degree. You know the independence number because you don't have a red G, right? So this gives you for free that the blue independence number is always at most K. And I will need it to have a big enough number of vertices. So let me tell you why we can find such a thing. So the statement is that there exists a set B, which is a subset of our vertices of Kn, such that its size is, let's say it's equal to M, which should be at least the total number of vertices over 8 to the K. And remember, we work with a big exponential or 2 to the 7K, whatever. So this is kind of a tiny bit. It's still pretty big. And it should have minimum blue degree, at least 7/8 M. Okay, so 7/8 of the total number of vertices in this set. Now, why can you find that? It's not obvious, but we'll use this two-pass Ramsey proof, which is just a generalization of what we did in Erdos-Moser and what you do for a usual Ramsey and what we did in this Kováry-Sós-Turán in the greedy argument. So it's called the two-pass proof. And the idea is that you do the following. If you can find a vertex which has red degree at least n over 8, take it. So suppose that we can find a vertex which has red degree in our big graph at least capital N over 8, then take it, delete all of its other neighbors, and do it again. Go into the neighborhood. If there is a red vertex which has degree n over 8, of the 1 over 8 proportion of the remainder, take it. It should still have n over 64 red neighbors, and keep doing that. If you do this for k times, what you constructed is a red clique of size k, because this vertex is connected in red for everything that you look afterwards. So all these edges are red. The second one is also connected in red to everything that comes after, and so on and so on. So a few probably. So this doesn't run for more than, so this needs to stop before you do it k times. So the size that you're left with is n over 8 to the k at least. What is the first thing? And when you get stuck, your red degree is at most, your maximum red degree is at most 1/8. So you have your blue degree at least 7/8. So you can find this mostly blue set and you're happy, or well, happier than before. Very good. So let's now see how to use it. So it will play kind of a role of an absorber if you wish, although it's a bit of a stretch. But we use absorption on it. But anyway, so what we do on the leftover is we take maximum vertex disjoint collection of blue H's. So this is the same idea as we did before. And let's call this set T for tileable. You can always tile it with blue copies of H. That's what I want for T. And then we're left with the leftover part, which we call C, and which will correspond to this kind of left part C. And what do we know for it? We know it has no blue H and no red G, right? The whole graph doesn't have a red G in this picture, and we've put every blue H there. I mean, if it had a blue H, we would have moved it there. So in particular, it's not too big. It has size at most Ramsey of G versus H, which is at most Ramsey of KK, which is at most 4 to the K. So kind of it's a smallish set. Good, but and also we know that our blue set is predominantly blue. So now I need to clean up this picture a little bit, and after that we'll be practically done. So what I'll do is, let me write it and then explain. So move any blue H which lives inside of B union C and has at least one vertex in C to T. Okay, so let's look at the picture again. I guarantee that in this part there is no blue H's left, but I might have some of them. I will have quite a few of them here, right? Because this is mostly blue. So what I say is, if you can find a blue H, which is using at least one vertex from C, then just move it there. And why I'm doing that is because this part is tiny. So when I do that, I don't affect this one too much, right? So doing that will take out at most 4 to the K times K vertices from this part, because there is 4 to the K of them there, and each moves at most K from this thing. So what we'll know for this thing is, now after doing this step, we know that this is still at least like minus K times 4 to the K. And also for the minimum degree, we know that everyone lost at most this many neighbors. So the minimum degree is still big. It's still going to be 3/4 M, because M is a big exponential, and this is also going to be big. I'll write in a moment what we want. Very good. So now I claim that because of this cleanup, there can be very, very few blue edges in between B and C. And let's see why that's true. So in particular, any V which lives in C has blue degree to B less than 4 to the K, I claim. Why? Suppose that it had blue degree of at least 4 to the K here. And remember that we know that there is no red G in our graph. So that means you have a blue H there. If you have a blue H there, kick out one of its vertices and replace it with this guy. He's connected in blue to everything. You can substitute, you get a blue H which is using this one, right? So we moved all these things. It cannot happen. So this is true. And it tells you that the total number of blue edges between C and B is tiny. Well, tiny meaning 16 to the K. Right, so this is at most 4 to the K. Everyone sends at most 4 to the K edges. So in total, that's most 16 to the K blue edges. So let me now draw a new picture. It's about time. The trick is to remember to do it before you start moving the upper. So now why did we do all of this stuff? Well, it tells us that most of the edges between B and C are red, right? So that brings us a bit closer to that picture that I just erased, the extremal one. So we have our B, which still has, I just deleted things I didn't want to, anyway, it's still big. It has big blue degree, and we have this stylable set T, which is styled in blue H's. And we have this leftover bit, and we know that there is relatively few blue edges in between. So let's just, so note that you can have at most 16 to the k vertices inside of here, which can have any blue edges going there, right? In total number of blue edges between here and here is 16 to the k, so you can't have more than this many vertices which see even a single one. So this tells you that everything else in between this blue part and C is completely red. Okay, and why is that useful? So let's say that I have at least alpha vertices here, and you can do that because if you remember, this was n over 8 to the k. So if this is why I took 8 to the k times 16 to the k vertices. You also gain a little bit because this is actually, but anyway, you have at least alpha, tiny number of vertices here, but that's going to be enough. Why? Because I claim you cannot find the red G prime from our family here. Because if you could find the red G prime here, well, you can just use your independent set here. All the edges in between are red. And well, it might be smaller than alpha, right? It needs to match whatever this guy wants. But it's smaller than alpha, you can, all the edges in between are red, you get a red G. We say that doesn't exist. So this thing has no red G prime. So we made it a little bit smaller and guarantee that it's a little bit smaller. And it still has no blue H, right? Because this is how we built it at the beginning. We put any blue H inside of T from the left over. So the size of C is at most this Ramsey of D of G versus H minus 1. And this now tells us that B union T has size at least n times the size of H, because the total number of vertices we're working with is this plus this. And we're done now pretty much because we can perfectly tile T. And this B has all the conditions for our lemma that I proved in the first half. It has like independence number in blue at most, well, k less than k because there is no red G. It has minimum blue degree, at least 3/4 m, 3/4 the number of vertices there. And it has at least, even we used already that it has more than 16 to the k vertices, so way more than 4 to the k cubed that we needed for the other one. So size of B is still big. So the lemma tells us you can decompose kk tiling in blue of B. And that means you can tile T union B perfectly, and you have enough vertices that means you will fit n disjoint ones. We get the contradiction, we're done. So
but if this is the only way you use absorption, even an asymptotic result would be fine here. I mean, it's just
no, so
if you want equality.
So the problem is you need the perfect one. Like this, if it's equal to n times h, you need really a perfect decomposition.
Just because you want equality, but if you didn't care about the eyes.
I think you might run into a bit of trouble, but maybe I didn't. I mean, yeah. So we had some easier asymptotic results before, at least for the cliques, but somehow we came to this. But yeah, I mean, I'm not saying. I mean, it's possible you don't need absorption for this, but this is really
the time understood the proof.
okay.
A way to do it.
So it's a kind of strange argument for Ramsey theory, but uses some kind of ideas, and I like it and hope you liked it. So let me stop here and thank you for your attention.
If you liked it, yeah. Questions?
You mentioned that this was known for sort of paths and cycles,
If you take multiple copies of paths and cycles.
or a single path or cycle. When you wrote sort of things we know, I was curious.
So this is the without copies. This is just yeah. So these are old results from 1960s.
Curious, what are the bounds? I mean,
They are linear. So this is also actually Jeff Kahn told me at some point. It's a very nice question. Do we know Ramsey numbers for anything which is not linear? So this is also linear in n in the size of the thing. Kind of even asymptotic versions. I mean, yeah, it's kind of embarrassing that what we know about Ramsey numbers. And I mean, it makes it interesting in some sense. It's a lot of things to try to do better. So maybe, like, I just didn't find any to answer him, but if someone knows, or in the cloud someone knows, I would be very happy to hear if there are bounds that I wasn't aware of. But thank you. It's, I mean, so what exactly there, I think maybe for, I mean, I'm guessing now, but it's something like 3 halves and maybe for either one, for paths or cycles. And yeah, so I can send it to you, but it's just linear and small constant. And there is a conjecture what should happen for multiple colors, but even for 3, we don't know. We know it just because it's 2 colors. And then it's a very nice result of, I also don't remember.
More questions? Okay, thanks.
Thank you.